So, hello everyone. So, I think people will join, but it's already 6. So, let me start today's session. Anyways, it will be recorded and you will find the recording in the YouTube channel. And if people tries to join in between, I shall let them in. Okay. So, welcome to the course of structural biology discussions, weekly discussions. And today is the week 8 discussions, and we are continuing it for the last 7 weeks. So we today what we will be talking about is the different spectroscopic techniques. So, in a nutshell, what we have discussed till now is the basic biochemistry techniques which are important to visualize the structures, basic cloning techniques, and then we went forward to look into the different 3D imaging techniques where we can get the three-dimensional structures of the proteins or any biomolecules using X-ray crystallography. First, we discussed about X-ray crystallography. What are the different means processes involved in X-ray crystallography, what is the theory behind it, and in the last 2 weeks we discussed about another technique of solving the three-dimensional structures of biomacromolecules, that is nuclear magnetic resonance, that is the NMR spectroscopy. Okay, so from the last class only you heard the term NMR spectroscopy, but we didn't go into deep about the different spectroscopy techniques. NMR is a spectroscopy technique, but today what we will be visualizing is a general view or general outlook about the spectroscopic techniques. I will give you a taste of spectroscopic techniques along with means what is the difference between spectroscopy and microscopy, and what are the different spectroscopic techniques that people utilize normally for means visualizing some very important informations or detecting some very important informations of your compounds or molecules using different spectroscopic techniques that we will be looking into. Okay, so not wasting much time. And if you people have any doubt, since no one has joined till now, so if you have any doubt, just like I say every week that we can discuss, so you can actually write to me or you can come in the next week and ask me about the assignments or any doubt regarding the course of structural biology. Okay, so yeah, someone wants to join. Yeah, okay. So, so today we will be talking about the different spectroscopy techniques. So before that, if you have any doubt, you can ask me. Uh, Shani, if you have any doubt, because others have not joined, so if you have any doubt, you can ask me. Yeah, yeah. Week 7 assignment questions, you are telling. Hello, hello. Am I audible? I was asking you week 7 assignment questions you have done. Yeah, yeah, exactly. Means Shani, you have pointed out correctly. So I was also when looking into the assignments, since these assignments are not set by me, that is set by sir and his group. So I don't have control in these assignments, but I also looked into the questions and I found two of the questions. So that was not the options were not correct. So I shall write it to the NPTEL team about this issue, and let's see what. Yeah, yeah. So what they did they said anything about this? Means what is whether they will consider you have been, yeah, they have not yet sent you. Okay, so I will write to them. So I will write to them about the questions. Which questions have you doubt? So today we will be discussing those questions as well. So can you tell me? I am showing you the questions. You can see my screen, right? In the PowerPoint slide. Okay, so in these four questions, you don't have any doubt. Okay, so then you have doubt in the fifth question, right? Fifth and eighth. Okay. Yes. So fifth and eighth. So eighth, you think that the answer can be A, option A also, right? Or what is the doubt about this? Yeah, so means there is a range, right? Between that range, this alpha and beta splitted sheets come. So what they have given the four options. So means both of them are partially correct. You are telling because of the slides in the slides what sir has written. So there from that you are actually telling, but actually both of them are correct. I can tell that because there is a range in between this alpha helix and beta sheets and this m degree values they come. Okay, so this is not like that a particular wavelength, but it may vary by one or two, but that is between 216 218. Okay, so both of them should be correct, and also then 2217 nanometer. So all of them are very close, mostly the A and C option. Okay, and also in the sixth question you don't have any doubt. Beer Lambert's law states that. So this question I found that this is not that much clear. So what answer did you give? In B.R. Lambert's law states that you gave A option, right? But means this intensity of light. So that is not clearly written. That intensity of light what means intensity of light absorbed or Oh no no, this is correct because what you said that is not correct because when we will discuss Beer's law, Beer-Lambert's law, you will see that this absorbance. So how can you tell that this epsilon value is inversely proportional to concentration from the equation of A equals to epsilon Cl? I think you are guessing from there that this is inversely proportional, but that is not the case because the absorbance is not constant, right? Absorbance will vary. So when you try to derive some means relation between two variables, one should be constant. So absorbance will be different for different matter, right? So from that equation you cannot tell that epsilon is inversely proportional to concentration. Epsilon is means this epsilon value is molar extinction coefficient is solely dependent on the type of the matter, means intrinsic property of your matter, as well as the wavelength that you are using for that experiment. Okay, so that's why this is okay, so it should be lambda. It is correct. Means it should be lambda, wavelength only. Concentration you cannot say because just the way I explained that from A equals to epsilon Cl. So there means absorbance is also varying, right? Absorbance is not constant. So if you want to like for you can tell from Beer's law that absorbance is directly proportional to concentration and directly proportional to the path length. Why? Because the epsilon value for a particular matter or a particular molecule is constant unless you change the wavelength. Okay, if you have a constant wavelength, that particular matter will have a particular molar extinction coefficient. So that's why epsilon becomes constant there. Then then you can tell that absorbance is directly proportional to concentration and directly proportional to path length. But that does not mean that epsilon value is inversely proportional to the concentration. You got the idea, right? We will be discussing. Yeah, depends on that particular substance intrinsic property as well as the wavelength that you are using for your absorption. Like in UV visible UV. Yeah, Exactly. It's like you are telling bonds, or it can be like different functional groups. Like one can have like OH group, one can have COOH group. So different functional groups in chemical in chemistry, if you see. And if for proteins, you may say that some have more alpha helix, some have more beta sheet. So they are absorbing in a different way. Okay, if you give different wavelengths of light. Okay, so this molar extinction coefficient is solely dependent upon the intrinsic nature of your matter. So today I will be discussing about this in brief. Okay, so you will get the idea there. But I also had one doubt. I don't know means because this question was also not clear. Beer-Lambert's law states that intensity of light means what intensity, whether the means intensity of light that is absorbed or the intensity of light that is emitted. Okay, so if it is intensity of light that is absorbed, so then it can be this the answer can be correct. Okay, and if the intensity of light that is emitted, then it will be wrong. Okay, so uh, that that is not clear. So this question, if you consider it intensity of light absorbed, then that is directly proportional to sample concentration, then it is correct. So I thought that many of you may have doubt in this question. So mainly the fifth question and the eighth question. Fifth question, it is wrong. The options are wrong because they have asked in correct decreasing order of wavelength. So the option A, which is given as the correct answer. So the greater than sign is wrong because X-ray does not have a greater wavelength than the ultraviolet. So it should be means it should be less than. The greater than sign should be less than, but again it will be an increasing order. So the correct answer will be radio wave greater than infrared, greater than visible, greater than ultraviolet, greater than X-ray. Okay, so that's the reverse of it. So about this, I will write to them, and let's see by next week. I think they will reply what to do, and I will let you know. Okay, and I will also tell them about this eighth question. Actually, I don't set up this question, so that is set up by sir and his team. So in IIT Roorkee, I think. So my work is to discuss with you about the week summary and also give you some practice questions that has been asked previously. Okay, so that is present in each of my slides. So I don't have control in editing these questions, and so what I can do is I can just write to them that, sir, this is not, I feel this is not correct. Can you rectify and please provide if someone has given some wrong option in this question, because the question options are wrong itself, so that person may should that should he or she should get marks in this question. So by that I can write to them. So I will do that. Okay. So other than these assignment questions, do you have any doubt? uh, Okay, so then what we can do is that we can just discuss about means the spectroscopy part, because last time I discussed only about NMR, so it took a lot of time. So then I couldn't discuss about spectroscopy. So we will discuss about spectroscopy, and I think much of your doubt which you have in this week's content, that will get clear. Okay, so let us start. So, as from NMR spectroscopy, there also we have heard the term spectroscopy. So, spectroscopy, from there, if you divide these two terms, there is this term of spectrum. Spectrum and study of that spectrum to decipher some chemical or physical properties, chemical properties, not physical, chemical properties of your matter. So if you use something to actually use the property of light that can actually interact with your matter and give certain properties by which, if you detect it quantitatively and try to visualize that or try to get that quantitative information, you can actually tell some chemical intrinsic properties about that matter. Okay, so that we were doing for NMR also, because we know that for every nuclei there was some nuclear spin, and due to that nuclear spin we were giving some radio frequency pulses, and we were seeing the energy gap between them. We were detecting the energy gap between them, which is a kind of spectra for different elements. For specific elements they will have different energy gap, and on the basis of that we were getting some information which were helping us to know about the intrinsic property, like how a molecule interact with another molecule, okay, inside that system. So those informations we were getting from the NMR spectroscopy. So spectroscopy can be have mainly two arms, that is energy absorbed and another one is energy emitted. Okay, energy absorbed means, as you know that we will also discuss today, that if you consider an atom, and this, inside the atom there are these protons, neutrons and electrons. Electrons are revolving around with the nucleus. The nucleus is composed of these protons and the neutrons, and these electrons are moving in certain orbits, and which each orbit is of some energy level, and they are quantized by the quantum theory. If you know, you will know from the class 12 knowledge. So, from if these electrons get some energy, it will try to jump from their ground state, that is from the lower energy state, to a higher energy state, because it can actually cross that barrier of energy, of two energy, between two energy levels, because of the external energy supplied. Now, no system wants to be in an excited state. It wants to come down after some time. If you are not giving that extra amount of energy, the electron will try to come again to its original position in the ground state, and it will emit certain energy while doing so. Okay, so that is the emission procedure. So this spectroscopy is based on these two arms. One is your absorption, another one is your emission. And how this, when you actually interact this light with certain matter, there may be different phenomena happening, which will be dependent on the wavelength, or the intrinsic nature of the light that you are using, as well as your matter. Okay, so what are the different phenomena that can happen are this, uh, these phenomena, like the light can come and it can reflect back, that is reflection. They can also transmit from the through the media, okay, by changing some their path length initially during the during the travel inside the media, and then also we will get the transmitted light. Then it can be totally absorbed. The light can be totally absorbed by the matter, or there can be some scattering, okay, by the by this matter. So that depends upon what kind of nature of the light that you are using, as well as your intrinsic nature of your matter. Okay, now these spectroscopic techniques means, what we do is that we actually make utilize these properties of the light while interacting with your matter, and we will try to quantify them, so that this will be differing. This all these phenomena will be differing in inside a matter as well. Okay, so matter to matter it will differ. It will be different, as well as inside the matter also, if there are certain change in chemical functional groups or chemical properties, you will see different phenomena for that, and that is will be characteristic to your matter. So what we will be doing is that we will be quantifying this phenomena and try to visualize the chemical properties of your matter. And this field of study is useful in various fields like agriculture, food, cosmetics, pharmacy, chemistry. Okay, so from so this is a very everlasting evolving field of science, or physics. From physics we can actually the spectroscopic terms came. So the first thing was that there I am discussing some history about this spectroscopy, because this was discussed also in such slide, and I have given this in a gist, so that you can just look into it, and if some questions are asked regarding this in your exam, or means in your exam, then you can actually answer it quickly. So you can understand this in the form of a story. So the first thing is that in spectroscopy, what is important is the light source from where this light will come and interact with your matter. So in the starting, when the science was evolving, people used to think that light is a kind of matter. So light is something which is actually helping us to visualize some other objects, and light is also an object. So they consider light as a matter, and they think that this matter is present throughout in our universe, and when we actually try to focus this matter through the help of certain lenses, we can actually visualize objects. So from there, John Kepler, Wilbur Snell, and Galileo Galilei, so they actually tried to visualize very distant objects by making use of this light, by making the telescopes. Okay, so they were working on how we can actually visualize different distant objects which cannot be visualized by our naked eyes. With the help of certain lenses or some combinations of lenses, we can visualize them. So at that time they used to wonder that light is a kind of matter. Okay, then then Sir Isaac Newton, he actually showed that light has some particle natures. Okay, and the light can be actually broken down into several components. So it's not like that light is a single matter. It can be broken down into several components. Like if you pass the light, a visible light inside a prism, while it will come and emit into different wavelengths of light and form the Vibgyor. Okay, so for the first time, Sir Isaac Newton, he actually showed that these lights are made up of means certain. He actually gave the idea of this means corpuscular theory or the particle theory of light. Sir Isaac Newton, he actually mentioned about that. Then actually there was a debate when Christian Huygens, Thomas Young, and Augustine Frenzel, they actually proposed that no, light is not only made up of matter or particles; it has a wave-like property. So they did. There was the starting of this wave theory of light. Okay, so later on, when so there were two important scientists who gave an understanding of what is light as a whole. So there two information. These two scientists have revolutionized this field of spectroscopy. So one is James Clerk Maxwell. So he actually supported by different experiments that no, that he supported the wave theory of light. Okay, and Albert Einstein. So mostly when we heard the name of Albert Einstein, we always imagine that the theory of relativity and general theory of relativity, special theory of relativity. But one of the finest work that Albert Einstein did, and for which he got Nobel Prize, is the photoelectric effect. Okay, where he showed that the light has a particle nature. So ultimately, it was clear that this light has both a particle as well as a wave-like nature. Okay, but till now, what people have done is that they have now gained some idea what is light. Okay, but they have not gone into deeper how we can use this light to just not to visualize the objects, but also to find out the intrinsic nature or the chemical integrity of those matters. Okay, so for the first time, Joseph Fraunhofer, G.R. Kirchhoff, and Robert Bunsen, they actually proposed an instrument which they named them as spectroscope. Okay, so why, from where this spectroscope idea came is that Fraunhofer, what he did is that when he tried to pass this solar means he had a matter and he allowed the solar rays to hit into it, and the solar rays got reflected and he collected in a detector. Okay, and he could see different bright bands, dark and bright bands in the detector. Okay, and he observed that for different kinds of matter, this band pattern was different. So he actually noticed that and he found it quite interesting. So from there, they actually got the idea of this spectroscopic method, and they actually launched the field of the spectroscopy. Now, one of the important concept that one should be clear to your mind is that what is the difference between microscopy and spectroscopy? Because both of these fields are dependent on how the light rays are interacting with your matter. Okay, so both of these fields are dependent on the light interacting with your matter, and how this interaction is giving some fruitful outcomes like different phenomena like transmission, deflection, and other things that we discussed in the previous slide. But the major difference is that in microscopy, the absorption and the emission that is been done by these compounds, they are actually used to visualize those objects. So in microscopy, we are more in the qualitative aspect. We need to visualize the matter or the object. Okay, but in spectroscopy, what we want is that we are more interested on how this matters, how the different atoms or how the constituents of these matters are connected to one another, and how they are interacting with one another so that they are giving some chemical function, or what is the chemical nature of that molecule, that we can quantitatively find out with the help of spectroscopy. So spectroscopic measurement is more of a quantitative measurement, whereas in microscopic measurements are more qualitative to visualize those objects. Okay, so under microscopy, so this image is a very important image, I will say. Why? Because it will give you a very means a lot of information in a very small period of time. Okay, so there are different types of microscopes. Okay, and this crystallography that we actually discussed in the start of our discussions, as well as electron microscopy that we will be discussing in the future sessions, as well as the normal microscopy where we can actually visualize the means our very matter in the micron level. Okay, then there is this thermography and radar. So as you increase the length means the dimension of your entity, there are different kinds of microscopic techniques that has been evolved that can be actually used to visualize your objects. In spectroscopy, so there are also different kinds of spectroscopy like X-ray spectroscopy, UV visible spectroscopy, IR spectroscopy, Raman, and the nuclear magnetic resonance spectroscopy. So each of these spectroscopic techniques give you some important results due to which you carry out those techniques, right? So this X-ray spectroscopy, these are very important to actually analyze what kind by what kind of elements your matter is made up of. So this elemental analysis is can be easily done with the help of this X-ray spectroscopy. So in X-ray spectroscopy, as I said that in the spectroscopy, it is always most of the times you will see that there will be an incoming energy, and that energy will be absorbed by the electrons, and that electrons will be going from the lower energy state to higher energy state, and then coming back to give an emission spectra, and when they are going from the lower to higher state, they will give you an absorption spectra. So this is the general overview of the spectroscopy. Now, which kind of electrons? So you know that there are some electrons which are the innermost inertial electrons which are near to your nucleus, and there are some electrons which are present in the outer shells. Okay, so normally in X-ray spectroscopy, it is the innermost electrons which get excited and go to the higher energy level. Okay, then comes the UV visible spectroscopy. So UV visible spectrometers, you will see that any chemical reactions or to actually visualize the the nature of a molecule, like for DNA, RNA, proteins. We all use this UV visible spectroscopy in our lab. So here from the from in the X-ray spectroscopy, from the name itself, the source, the wavelength that is used for excite those innermost electrons are the X-rays. Okay. In UV visible spectroscopy, you have this UV and the visible range of wavelength that is actually used to excite the electrons which are mostly present in the outer shells. Okay, so in the outer shells, those electrons are present, they will be excited and then they will provide an emission as well. So that is UV visible spectroscopy. We will discuss about UV visible spectroscopy in details. Then comes the IR spectroscopy. So in IR spectroscopy, that is the infrared spectroscopy, you actually visualize, or you actually make the use of the molecular vibration of the atoms. Okay. So if you imagine that in a space or in a matter, like if you imagine this as your water molecule, it is made up of two hydrogen atoms and the oxygen atom. Okay, and with this hydrogen and oxygen is bonded by a bond as well as, so there are certain bonds and a bond angle, and due to the flexibility of this bond, means if it is a single bond, it can rotate freely in space. It is more conformationally, it is more rich, conformationally rich, whereas if you have more unsaturation, like double bond, triple bonds, then it will be more restrained. The conformationally, it will be more restrained in the space. So based on these different degrees of freedom that you have for a molecule in space, they will face certain molecular vibrations in the space. Okay, and that will be different for different kinds of bonds. Okay, so that molecular vibrations we can actually quantify with the help of this infrared spectroscopy, and it can actually tell you that what kind of chemical bonds are being formed between two molecules in the space or in a chemical compound. Okay, so from this IR spectroscopy, nowadays it is also known as Fourier transform IR spectroscopy. Okay, FTIR. So these are normally very useful to, if you are looking for any functional groups, means if you are interested to know about what are the different functional groups that are present in your compound, you can actually go for this IR spectroscopy, that is infrared spectroscopy. Then comes Raman spectroscopy. Raman spectroscopy means how this is about the molecular rotation. So if how these molecules are rotating in space, that means that is given by this Raman spectroscopy. Means we will discuss about Raman spectroscopy more in details as we will discuss today's slides. Okay. So in Raman spectroscopy, you can actually get the idea about the different molecular orientation in your compound. Okay, and finally the nuclear magnetic resonance that we actually saw in the last class, they actually mostly they are used for giving you the molecular connectivity, means how one molecule is connected to another molecule in the matter, that can be visualized with the help of this NMR. As we discussed that that coupling shifts all those things, the scalar couplings through the bonds, how a spin system can actually affect another spin system, and the nature of another spin system. So basically how the chemical environment around that atom is changing, that we can actually get the idea from NMR spectroscopy. Okay, so this is a nutshell about spectroscopy and microscopy. Now we are going more deeper into the source, that is the light, which we know that normally these are some electromagnetic radiations which which falls in this electromagnetic spectrum. Okay, so where if you see the radio waves, microwaves, infrared, visible, ultraviolet, X-ray and gamma rays. So when you move from this right to the, means from radio to gamma rays, the wavelength decreases, whereas the energy increases. As we discussed last class, that this energy and wavelength are inversely proportional, and also the frequency increases as we go from radio to gamma rays, but the wavelength decreases. So this is the electromagnetic spectrum. Now, the electromagnetic wave has two components. One is this electric field, and another one is its magnetic field. Both of them are perpendicular to each other, as well as they are perpendicular to the direction of propagation of this electromagnetic wave. So if you consider an x, y, and z direction, in x direction, if it is means if you consider a Cartesian coordinate with three axes x, y, z, and three of them are related to one another in 90 degree, means one in right angle to one another, then if you put the electric field in the x-axis, your magnetic field direction will be in the y-axis, and the direction of propagation of your wave is towards your z-axis. Okay, and just to brush up your knowledge, that is, if you consider the from one crest to another crest, the distance between them is your wavelength of that particular electromagnetic radiation. You can also calculate it from one draw to another draw. Okay, so that will also give you the wavelength. Now, as I said, that these electromagnetic waves, when they fall under to a particular substance, they can actually give certain emissions. Okay, they can actually do certain behaviors, like that, and they will give certain patterns which are known as the spectra. Now, the spectras can be of three types, that is continuous, absorption, and emission spectra, broadly classified. Okay, now, what is those continuous spectra means? You can imagine the example of your prism. When you are putting the white light through that prism, it will come out as different colors of seven different colors of spectra is coming, and they are known as the continuous spectrum. Now, if you consider an absorption spectrum, this means that if you are using a particular wavelength of light to excite a particular electron, those electrons which will actually absorb that particular wavelength of light, they will be moving, they will be absorbing that light and moving from the ground state to the absorption state, to the ground state, from the ground state to the higher energy levels. Okay, excited states. So during that phenomena, you will find that those photons which were being used by these electrons to go from the lower to higher energy state, so that photons are lost while detecting. So for that, you will, for the in the absorption spectra, you will see dark bands in a bright background. So these dark bands means there this absorption is taking place. But when it is the emission spectrum, you will find that there are certain distinct bands, bright bands in a dark background. Why that is so? After some time, when the electron has moved from its lower energy state to a higher energy state, it will again try to come down to its ground state. And while doing so, it will emit certain energy. And now we know that these states, these ground energy levels, these are all quantized energy states. That's why when during the emission, you will get this distinct quantized bands in the emission spectrum, that is bright bands in a dark background. So these are the three different kinds of spectra that we can get from by the interaction of your electromagnetic wave with your matter. Now we make the use of different spectrum for different kinds of spectroscopy. Now, this is the concept of basic concept of how the constructive interference that we were discussing from first class, that if two waves are in phase with one another, their amplitude will get add up to in the final wave, and it will give you a larger amplitude or larger intensity wave. Okay, so So now we are moving to the absorption and the emission spectra, and we will from here we will be actually going to the UV visible spectrophotometer. So ideally, what should happen? When you are giving an energy, for example, if you have this electron sitting in this ground state and there is this energy levels, the higher energy levels which are quantized. So you know that for the electron to jump from this state to this excited state, there is an energy gap of h nu, for example, and you are supplying the same h nu from the exterior so that this energy gap is now compensated and this electron can move from there here to the high energy state. Now ideally what should happen is that after some time the energy that you utilized for the electron utilized for moving from its ground state to the excited state, after some time it should come to the ground state by radiating that equal amount of energy that was being used for the absorption. So that is the ideal case, but that is not always true. From here, one kind of spectroscopy where there is this phenomena is not happening, where this absorption always the energy that you provide, the emission energy where it can be less or more, then this kind of where you utilize this information, that kind of spectroscopy falls under the Raman spectroscopy. Okay, so we will be discussing about Raman spectroscopy as well as in the future slides. Okay. So this is this phenomena, this absorption and emission phenomena. This is utilized by a spectrophotometer. This is an instrument that measures the amount of light that is absorbed or the intensity of color at a given wavelength. So how much amount of light is absorbed or how much intensity of light is absorbed, that is actually given by a spectrophotometer. Now, what kind of information it will give you? It will give you the transmittance and absorbance information. That is, how much amount of light is transmitted after it interacts with the matter and how much light is absorbed. So normally if you look into the spectrophotometer of your lab, if you someone of you are working in a biology laboratory, you will find that we often use this UV spectrometer. Okay, UV visible spectrometer. You will find that it will give you the absorbance value at a particular wavelength. Okay, so but how this absorbance is calculated, that is through by calculating the transmittance. So the instrument actually calculates that how much light is transmitted through after it interacts with your particular matter, and then it converts that transmittance to the absorbance because both of them are connected, as we will see that in the Beer-Lambert's law. Now, what is the basic setup of a UV spectrophotometer? You will have a light source, then you will have some collimator. Collimator means there are certain lenses which will focus your source light into a prism. So from the prism, which is also known as the diffraction grating, you will be, as we discussed just when we discussed about the corpuscular theory by Newton, that white light when passes through the prism, it gives you 7 different colors or vibgyor. Now, when these 7 different colors are falling, or these 7 different wavelengths, more specifically, falling on a wavelength selector, now you don't want all the wavelengths to pass and interact with your matter. So that is the beauty of the spectroscopy. If you use a particular wavelength of light, you can excite a different chemical property of a matter. Okay, so that concept we are utilizing. So there is a wavelength selector. So what are these wavelength selectors? These are some kind of filters. So in spectroscopy and microscopy, you will come across various filters like band pass filters, short pass filters, long pass filters. Means short pass filter means all of these filters. They, what is from the name itself, it shows that it is actually filtering out some amount of light or some wavelengths of light, or it is specifically allowing some wavelength of light to pass through while avoiding the other wavelengths to pass through it. Okay, So on the basis of it, several filters have several cutoffs. Like in the short pass filter, from the name itself, you can say that short pass means it will allow, there is a cutoff wavelength for that filter, and it will allow the any wavelength which is shorter than that cutoff wavelength to pass through it. Okay, that is why short pass filter. If it is a long pass filter, means any wavelength which is longer than the cutoff wavelength given for that filter, they will be passing through that filter, and other wavelengths will be not allowed to pass through. And the band pass means there is a range of wavelength that is given. For example, only 400 to 700 nanometer wavelength can pass through that filter. So there is a band pass, that is called as a band pass filter. Okay, so on the basis of this, you can select the several specific wavelengths. Then that will be your intensity, initial intensity, which will be coming and hitting your sample. Now, once it now some amount of this wavelength will be absorbed by this substance, and then the other light will be transmitted into a detector. So from here we can actually visualize that how much we can quantify that how much light is transmitted, because we know how much light was coming and how much light is transmitted by this intensity ratio. You can actually find out. Then from the transmittance, the instrument will calculate what is the absorbance by this media. So this is the overall general architecture of your UV visible absorption spectroscopy. Okay. Now, the example of what is the use of this UV visible spectrophotometer is, so in some kind of interview questions you can be asked, like, you have a spectrophotometer in with you, and you have been given three tubes. Okay, in one of them you have DNA, in another one you have RNA, and in another one you have protein, and we have not given any label in the tubes. You need to find out from by using the UV spectrophotometer that which sample is what. Means your tube A is DNA, RNA or protein. So how can you do that? Okay, so that is very easy if you know the basics about the UV spectroscopy. As I said that for all other, for different matters, there will be different kinds of absorbance at different wavelengths. Okay, like if you have a DNA, you know that in the inside the DNA there are certain nitrogenous bases. So it has been found that these nitrogenous bases, when you excite, means when you provide a 260 nanometer wavelength light, and when it falls into the DNA or any nucleic acid, these nitrogenous bases will absorb that 260 nanometer wavelength of light, more as compared to a 280 nanometer wavelength of light. Okay, so in 260 nanometer, this nitrogenous bases absorb more, absorbs more as compared to 280 nanometer. In 280 nanometer wavelength, the proteins which have the different aromatic groups like the tyrosine, tryptophan and phenylalanine, they absorb more in 280 nanometer but lesser in 260 nanometer wavelength. Okay, so we make this, utilize this property of the biomacromolecules to differentiate them in a UV spectrophotometer. So you know that what I said, that the nitrogenous base of the nucleic acids, they absorb more in 260 nanometer wavelength. So we will be exciting your tube A, tube B, tube C with 260 nanometer wavelength as well as 280 nanometer wavelength, and we will collect the absorbance at both 260 nanometer and 280 nanometer, and then we will take the ratio of 260 nanometer divided by 280 nanometer. Now what will happen is that for nucleic acids, the 260 nanometer wavelength will be higher, so the net value that we will get, that is greater than 1. Okay, because in 280 nanometer it will be less, and 260 nanometer it will be more, means the numerator is more than denominator, means the value that you will get, that is greater than 1. Okay, but for proteins it will be the reverse, because 280 nanometer absorbance will be more, so you will get the 260 by 280 value to be less than 1. That is around, for protein it is around 0.57 to 1. You can consider that it is a like a protein sample. Okay, now if you are doing for DNA and RNA, now nucleic acids will be greater than 1, then how to visualize what is DNA and what is RNA? It has been observed that DNA gives this OD 260 by 280 ratio for DNA is around 1.8, whereas for RNA it is more, it is around 2. Why that is so? Because in a DNA, this nitrogenous bases which actually absorbs your 260 nanometer wavelength, they are embedded inside their double helix, and they are not much exposed to the environment, so that they can absorb more. So that's why they are absorbing less amount of 260 nanometer wavelength light as compared to RNA, where your nitrogenous bases are more exposed. Okay, so they will absorb more 260 nanometer light as compared to DNA. So this is a simple experiment by which you can actually tell that your sample consists of DNA, RNA, or a protein. Okay, using UV visible spectrophotometer. Now, what is the theory behind this UV visible spectrophotometer? So that is given by your Beer-Lambert's law. Okay, so in the start of today's session, when we were discussing about some doubts about the assignments. So there we also discussed about this Beer-Lambert's law. Means Beer-Lambert's law is actually given by two scientists, Beer as well as Lambert. So there were two laws. One law forwarded by Lambert, another one by Beer. Then they combine those two laws to give you this A equals to epsilon Cl, that we know as the Beer-Lambert's law. What is Lambert's law? Lambert's law says that the intensity decreases exponentially with increase in path length. Means the intensity which of the light that is coming and hitting your matter, the initial intensity of that light decreases as you increase the path length. Means if normally your samples are actually visualized or detected with the help of this kind of cuvettes, and these cuvettes have a particular path length. So you put your sample inside this cuvette and put it into the spectrophotometer. So you consider that there will be certain period or certain length of this molecule of this cuvette in which this light is passing through this cuvette. That is your path length. Okay, and normally for there are 1 centimeter cuvettes, 10 centimeter cuvettes. So there are different kinds of cuvettes, and for a cuvette you will have a specific path length only. Okay, and so it is said that the intensity of the light that is coming, the incident intensity of the light, they actually it decreases exponentially as the path length increases. That is given, that is the Lambert's law. Beer's law states that the intensity decrease exponentially with increase in concentration of the media. So the intensity of your incident light, I am telling about incident light. Okay, so the intensity of the incident light that is falling into your cuvette, that will actually decrease with the increase in concentration of the media. So more amount of amount of matter or more amount of molecules that you have in this cuvette, it will absorb more amount of photons or absorb more amount of in light. So the final intensity that will be going from here to the detector, that will be much lesser as compared to the intensity, the initial intensity. Okay, so that's why it was said that intensity decreases exponentially with the increase in concentration of the media. Now, when you actually combine these two laws, you will find that the absorbance by the molecule which is present in your cuvette, that is directly proportional to your path length and directly proportional to the concentration of the matter which is present inside your cuvette. because this intensity, this initial intensities that is there, this initial intensity is also inversely proportional to your absorbance. So this absorbance is thus directly proportional to your concentration of the medium as well as directly proportional to the path length. So from there, when you actually remove this proportionality, then comes a proportionality constant, that is the epsilon value, which is also known as the molar extinction coefficient. And this molar extinction coefficient is a measure of how strongly a chemical species or substance absorbs light at a particular wavelength. So this is a measure of how strongly a particular matter is absorbing the light at a particular wavelength. Okay, so this molar extinction coefficient is dependent upon your matter on which you are actually trying to calculate the absorbance, as well as the particular wavelength with which you are trying to calculate the absorbance. Okay, so this is what we discussed in one of the question of your assignment. Okay, so it is an intrinsic property of the chemical species that is dependent upon their chemical composition and structure. So this is dependent upon the intrinsic property of your matter. And the SI unit of this molar extinction coefficient, as this absorbance do not have any unit, it is unitless. So from here, if you see, the concentration has a means this concentration has a unit of molar. Okay, and your path length have a concentration of centimeter, sorry, the unit as centimeter, and the concentration has the unit of molar. Now, if you see what is the unit of epsilon, that is, if you take this concentration and path length this side, it will be molar inverse, centimeter inverse. So the unit of your molar extinction coefficient is molar inverse, centimeter inverse, and your absorbance has no units. So now what we discussed, that this absorbance is actually dependent on your transmittance by this relation. Absorbance is equals to minus log of transmittance, and this transmittance is the I1 divided by I naught. So what is this I1? I1 and I naught. I1 is the intensity of light that is coming out, and I naught is the intensity of light that is going inside the sample. Okay, and this is also means the absorbance is given by this I naught divided by I. So also sometimes this I naught can be mentioned about, the I naught is the intensity of light transmitted through water. Means sometimes for always getting an absorbance, you need to see that your proteins or nucleic acids or anything, they will be in some medium, right? Like for a buffer, like in a buffer or in water. Now, when you are calculating the absorbance and you just take the absorbance of your sample, then the absorbance that is coming, that is the cumulative effect of your solution, means the solvent, as well as your solute molecule. But you only want the absorbance of your solute molecule, not the solvent. So then how to minimize it? To minimize it, you will have to do a blank absorption by your solvent itself. Like if it is water, then you take water and then calculate the absorption. Then you subtract that absorption from your final means the absorption of your solute plus solvent. So then you will get the absorption of your solute. Okay. So this is the basic of the Beer-Lambert's law. Now, UV visible spectroscopy. So, in UV visible, as I mentioned, that this energy orbitals are, the orbits are quantized, and there are different energy orbitals. Okay, and on the basis of this, there are, for UV visible spectroscopy, two kinds of orbital shift is actually visualized with the help of this UV visible spectroscopy. One is from N to, so if you remember this molecular orbital theory in class 12, so if there is a means gain of energy from the n orbital to the pi star, or from pi to pi star, then these energy transitions falls under the UV visible spectroscopy. By which I mean that the UV visible spectroscopy wavelength or the energy is corresponding to this two transitions, two molecular orbital transitions of the electrons. Okay, so the energy gap between them corresponds to the energy what is being utilized in the UV visible spectroscopy. Now, this is means the intensity of the absorption and the so this is for a fluorescence emission. Okay, this is a fluorescence kind of spectroscopy where you see that, as I said, that when you use a particular wavelength of light for the absorption, you see the emission is shifted. The wavelength it gave a higher wavelength, means a lesser energy of the energy is emitted from it. Okay, so you see there is this Stokes shift. Stokes shift means uh, every time when you see an absorbance, there will be a particular wavelength where you will have the maximum absorbance. That is given by your lambda max. Okay, so the lambda max value gives you the maximum absorbance. So similarly, there you will get a maximum emission at a particular wavelength. And if you subtract between the means the emission lambda max emission minus the lambda max absorption, you will get the Stokes shift. So this is known as the Stokes shift. Means you are getting a wavelength that is higher in corresponding to your original wavelength which is given for the absorption. Okay, and this compounds with lone pairs and multiple bonds with lambda max is equals to 200 to 600 nanometer. So this falls under this UV visible spectroscopy range. So any compound with this kind of absorption, that is lambda max value from 200 to 600 nanometer, they can be actually visualized, or they can be actually the spectroscopy which can be used for this is this UV visible spectroscopy. For just like the absorbance of a protein that we discussed, so if you see the molar absorptivity versus the uh, spectra, you see that there are different aromatic amino acids as I mentioned. One is phenylalanine, one is tyrosine, another one is tryptophan. Okay, and they mostly absorb at around 280 nanometer wavelength. So 280 nanometer wavelength, at around 280 nanometer wavelength, they will be actually absorbing, and mostly for phenylalanine it is 256, tyrosine it is around 270, and the mostly the tryptophan that actually as you see this the tryptophan actually absorbs more in this 280 nanometer. And once you find that, you actually take, this is a formula by which you can actually calculate the concentration of your protein in mg per ml from the absorbance. That is, you take the absorbance of your protein sample at 280 nanometer and 260 nanometer, then you put it the value here and subtract it, you will get the idea about the protein concentration in mg per ml. Okay, now, till now, what we have discussed around, here is this UV visible spectroscopy. Okay, so where the outer shell electrons, they are undergoing a transition from their lower energy state to a higher energy state, and you are getting that property, that absorption and emission, in the kind of certain spectra, and you are utilizing it for visualizing the functional groups of your matter. Okay, now we are going to another kind of spectroscopy which is known as the CD spectroscopy. So this CD spectroscopy is sometimes very useful for a lab which is working with the proteins. Okay, so to visualize the protein secondary structures, the CD spectroscopy is very useful technique. So what is the full form of CD spectroscopy? It is circular dichromism spectroscopy. Okay, so what is that? If someone wants to understand, is that just like the different wavelengths of light when falling on a particular matter, they provide different kinds of emissions and through which you were detecting in UV visible spectroscopy. Here what is done is that two the same wavelength of light, if it has two different forms, means if they have two different kinds of polarizations in them, one is left-handed circularly polarized light, another one is right-handed circularly polarized light. And if you use both of them into interact with your matter, they will interact differently. Means there is a difference between the absorption of the left and right-handed circularly polarized light by any proteins or any substance which you use for the CD spectroscopy. So now one question should come to your mind is that what are these polarized lights? Means what is this right-handed polarized light and what is this left-handed polarized circularly polarized light? So for that, let us understand that phenomena first. Okay, as I mentioned previous few slides above, that your electromagnetic wave has two components. One is your electric component, another one is your magnetic component, and they are perpendicular to one another. Now if you consider any one of the component, for example the electric component, and forget about the other component for your ease of understanding. So that component, if you consider this as your xyz, so that component, the electric component, can be perpendicular in the y direction, that is in a vertical direction to the direction of propagation of the electromagnetic wave, or it can be in a horizontal direction as compared to the direction of propagation of that electromagnetic wave. So these kind of waves which are where this electric component, for example, is in a vertical direction as compared to your direction of propagation, they are known as vertically polarized light. And those which have this horizontal, in the horizontal direction you have these oscillations, they are known as horizontally polarized light. Now when you have a light, it has both this vertically polarized as well as horizontally polarized light. If you take, if these two waves are in phase with one another, phase means in phase with one another means wherever it has a crest, this wave should also have a crest in the same position. Okay, so in the same time period, so then these waves are in phase with one another. So if these two waves are in phase with one another, then the resultant wave, the is in 45 degree with respect to these two waves, because if you consider this is the one axis and then this is another axis, the resultant vector between them is in between them, that is in between them is the 45-degree angle. You will have this linearly polarized light. Means you see this the wavelength of the light is not following a particularly vertical polarized light or a horizontally polarized light. It is a resultant between these two. Now if you consider that this kind of linearly polarized light will be present in all the directions, and in like for example if you see this figure, so it is pointing out in all the direction, and in every direction it will have equal intensity, and in the if you consider that this will polarization will not be happening in a normal electromagnetic wave, because this will cancel out each other, because one is in the positive direction and another one is in the negative direction. If you see in the 360-degree rotation, so this resultants will come in the so there is a positive direction resultant as well as in a negative direction you will also have a resultant. So depending upon the direction of your vector. Okay, so in a light source you will have all those combinations and they will cancel out one another, so that this is not a polarized light. Okay, but this light, this electromagnetic wave, when passed through a polarizer, it will allow only a particular wavelength of polarized wave, linearly polarized wavelength of light to pass through it, and others will not be allowed, just like you see here. So you have these different means propagation of wavelengths in 360 directions and 360-degree angle, and each one was cancelling each one another, and you were not getting any polarized light. But whenever you are passing it through a polarizer, it will allow only one direction of light to pass through it, and other linearly polarized light in other directions will be stopped here. So with the help of this, you are creating a linearly polarized light in one direction. So this is the example of a linearly polarized light. Now what we discussed here is a circularly polarized light. So what is a circularly polarized light? I mentioned you here is these two waves, the vertically polarized light or horizontally polarized light, these two are in phase with one another. In a linearly polarization, these should be in a phase with one another. Now, what if they are not in a phase with one another? They are out of phase. For example, this red color wave and green color wave, they are not in phase with one another. Means they are the position at which it has a crest, it does not have a crest. Instead, it has a trough or some other means the waves are not phased with one another. Now, if you consider that what will be the resultant of these two waves, it will not be in a straight line like you have seen for this kind of linearly polarized light. So here what will happen is that your light will be moving in a helix because these two waves are not in phase with one another. So the resultant wave that will be coming, that is in a kind of helix. Okay, so that's why, and when you actually pass two means polarization, a linearly polarized light to another means one by four wave plate, what it is doing is that means here they are lagging by one by fourth of wavelength. Means whenever you have any four phase difference, that is actually given by that how much in how much by how much wavelength one wave is lagging the another or leading the another. So if you see that if it is 1 by 4th, the wavelength of this is 1 by 4th of the wavelength of vertically polarized light, then this circularly polarized light, this helix like movement of the light occurs. Okay, how to generate it? First, you need to generate your linearly polarized light through a polarizer, just you have seen for this. Now, if you put a film which is known as 1 by 4 wave plate, which retards in one direction the vertical, for example, the horizontally polarized light is retarded by 1 by 4th wavelength, then it can actually form a circularly polarized light. So from the linearly polarized light, you are getting a circularly polarized light. Now, this circularly polarized light can be in two directions. One is clockwise, so this is moving in clockwise, or it can move in anti-clockwise direction. Okay, so on the basis of in which direction this electromagnetic wave, the circularly polarized light, is propagating, it is known as right-handed polarized light or a left-handed polarized light. Okay, so in right-handed polarized light, it is clockwise. In clockwise direction, it is moving. In left-handed polarized light, it is moving in a anti-clockwise direction. Now, what people found out is that when you pass through this right-handed polarized light and the left-handed polarized light in a matter, the matter will not behave the same for both of the polarized light. So there is some kind of difference in the absorption of this right-handed polarized light as well as the left-handed polarized light, and we actually make use of this difference of absorbance in the circular dichroism spectroscopy. Okay, so this CD, the circular dichroism spectroscopy, measures the difference between the absorption of light and of left and right-handed circularly polarized light. So that is the difference in the absorptions at a particular wavelength of light that is given by the absorbance and for the right-handed circularly polarized light subtract minus the absorbance of the left-handed polarized light at a particular wavelength. Now, from the Beer-Lambert's law, where we actually found that this epsilon A is epsilon CL, or here it is written epsilon BC, B is the path length. So if you put that value here, so there is a molar means this molar extinction coefficient for right-handed polarized light as well as the left-handed polarized light will be different. So if you subtract them, and then if, because that is because of the intrinsic nature of that property, that or that matter, intrinsic property of that matter, the chemical composition of that matter, due to which it is behaving differently for different circularly polarized light. So that's why you have two different epsilon values. If you subtract them and multiply it with the path length and the concentration of your sample, you will get this delta A value. Now this delta A value is given by, also sometimes this delta A value is represented by this ellipticity. Okay, so this delta A value is of very less value. Okay, so this is a very less amount of value. There is a very minute difference between the absorbance in the by the right-handed circularly polarized light and the left-handed circularly polarized light. What is this theta, which is also known as the ellipticity? This is when I was telling you that it moves like a circularly polarized light and it is like a helix which is forming. So it is not a circle because of the difference in the means wavelength in two different directions. That is, one wave is lagging, another direction, another wave in another direction. So that's why you will not get circles. You will get here ellipse, and you know that for each and every ellipse there is an angle. Okay, so that angle is given by this theta value, which is also known as the ellipticity. Now this ellipticity is related to the absorbance, the difference in absorbance by this formula, and since this absorbance is very less, this theta value, this ellipticity of a particular of a particular matter or a particular substance is actually given the unit of millidegree. Okay, so it is 1 by 1000 times of your degree. In that level you actually get the difference. So if you want to see that what is the difference, so this is the table that actually I gave you, and from here you can say that this is 260 nanometer, but you actually in the question there is written the 218 nanometer. So I checked that there can be some in between 215 to 220. There can be this absorbance of the beta sheet, but more precisely it is more towards the 218 nanometer if you see in the Google, but it 216 is also not wrong. Okay, so that I will be writing to them so about this doubt, and if they actually tell me how to means if I can contact sir, then I can also discuss with him about this doubt. Okay, so what I wanted to show you is that for different secondary structures of a protein like alpha helix, beta sheet, random coil, you have a characteristic CD spectroscopy pattern. For means for beta sheet, you have two different this means bands. What you are saying that milli-degrees at two different wavelength, you will have this peaks. Okay, for alpha helix, it has a characteristic different pattern, and for random coil, you have only a negative band. Though positive band is present for a random coil. Okay, so for alpha helix, it is given that 222 to 208, 192 for positive band also, and it's in alpha helix. 1 minute, someone wants to join. Okay, so so what we were discussing is this. Sorry. So we were discussing the CD spectroscopy. So here you can see that there are characteristic patterns of different means uh, uh, for beta sheet you have a characteristic pattern of CD spectra. For alpha helix you have a characteristic pattern, and for random coil you have another characteristic pattern. And all these wavelengths are important so that means you can see in your assignment also they have asked, and it may be asked in your exam. So you can actually look into it and try to memorize it to a level so that if these kinds of questions come, you can actually answer it. Okay, so um, this is about this CD spectroscopy that we talked about. Now we are going to more into the fluorescence spectroscopy. So we will touch little bit about the fluorescence spectroscopy and then the Raman spectroscopy. So in the fluorescence spectroscopy, what is mostly used is some fluorophore, right? So for fluorescence spectroscopy, what is important is that you have certain fluorophore. So what is a fluorophore? Fluorophore means when you are giving a particular wavelength of light, it will actually absorb that particular wavelength of light and give emission, and that emission is in the form of a fluorescence. Okay, so that those are known as the fluorophores. So the most common fluorophore which actually revolutionized the means field of biology as well as this fluorescence microscopy or spectroscopy is this GFP, that is the green fluorescent protein. So the green fluorescent protein has been found in this jellyfish Aquaria victoria from millions of years. But how the scientists found out, so that is also a kind of inspirational story that you can actually come. You can you will always hear about this story because in experiments, if you want to pursue research in your career, many a times it will come that something is not happening, so you are getting some failures in the experiments, and sometimes as PhD scholars we get frustrated that the result is not coming, so the in PhD, so the science is very tough, and so everything is doomed. But that is not the case. So there are some discoveries which has revolutionized the world, and that came from repeated negative results. One of the example is the green fluorescent protein. Another one is ampicillin, the discovery of ampicillin. Another story is this green fluorescent protein. Those scientists who was working for this GFP, and he also got the Nobel Prize. So this what he used to do is that he observed that these jellyfish always at night they actually fluorescence, they provide some fluorescence in the sea water. He actually saw that. So then he started his lab and he tried to means he want to extract that molecule which was responsible for this fluorescence in the jellyfish. So he took jellyfish, he corrected jellyfish, he actually prepared the cell extract from that jellyfish and tried to characterize that what is there which is actually giving this green fluorescent protein. And every time when he actually he's a biochemist, for example. So in biochemistry lab we always maintain a pH as well as a salt concentration, and we think that any protein will if we vary these conditions the protein may denature. So he actually used a neutral buffer as for example, and he was always when he is isolating these proteins in his lab, there was no fluorescence. So he was wondering that what is the case. I am seeing that this jellyfish is giving the fluorescence, but when I am doing and trying to isolate it in our lab, I couldn't see any fluorescence. So years after year passed, he tried to check and he got frustrated that okay, why it is not working, why that is so, if I am doing some wrong things. Then a student comes. So sometimes mischievous students are also very good for a biology laboratory. Not very good, but yeah. So for some students, so what they did is that they so he threw. He was working. The student was working, and he didn't find any fluorescence. So he just put that cell extract in a means in a dustbin where there was some seawater present. Okay, and he went home. Then next day, when the scientist came, he saw that there was something fluorescence from the dustbin. Okay, so he thought that what is that case? Then he asked that student, what have you done? How you are getting this fluorescence? He said that, sir, I had some sea water in that dustbin also, and in that I have put the cell extract or this protein. So then he understood that okay, so this protein will give fluorescence at higher salt concentration, which was being missed, which he was missing all these years. That's why he was not getting any fluorescence. So from there he actually started the discovery of this GFP protein. So this is a very inspirational story for those who don't get results, because sometimes not getting results also is a reason there is some scientific phenomena which is happening that you are not understanding. That's why you are not getting your result, but there is something which is going on. So don't get demotivated. You should always work and try to find why it is not happening. Okay, so this GFP protein has 238 amino acids, and each monomer is so it has a, you see the beta barrel like structure, and in between them there is a alpha helix. Okay, and there in between the core of this GFP molecule has a fluorophore, and mostly these fluorophores are being means there is a proton transfer which happens due to these three amino acids which are present, like that is serine 365, tyrosine 66, and glycine 67. So they actually help in means the proton transfer to a histidine, and which actually helps this GFP protein to fluorescence, to give fluorescence. Okay, now different so these are the specification that each monomer of this GFP is composed of an alpha helix surrounded by 11 standard cylinder of anti-parallel beta sheet cylinder, has a diameter. So if you see there are 11 anti-parallel beta sheets which are forming, which are perpendicular to one another and forming a beta barrel like cylinder, and that has a diameter of about 30 angstrom and is about 40 angstrom. Okay, so this means this alpha helix has a diameter of 30 angstrom, and the total compound is around 40 angstrom long fluorophore located on the central helix. So there is a 40 angstrom located means fluorophore in the central helix which is present in this GFP. So these are some specifications, and what is important for you to remember is that what are the amino acids which are responsible for this GFP fluorescence. Okay, so this serine, tyrosine, and this glycine 65, 66, 67. Now, scientists have once this GFP was discovered, so many people were trying to get into some enhanced prototypes of this GFP protein, which can give you more enhanced fluorescence. Like people were searching that, and one of them is this S65 to T. Means if you mutate this serine 65 to threonine 65, it has been found that the this wild type GFP is transformed into an enhanced green fluorescent protein, which is also known as the EGFP. So this EGFP has this mutation. This serine 65 is mutated by this threonine. Okay. Now, if you want to see, so here what we discussed is that what is the GFP, and I said you due to the fluorophore it is giving you the fluorescence. So what is the theory behind that? How we can actually visualize that what molecule will give you fluorescence and what will not. Okay, so every molecule is not a fluorophore, right? So the concept is given by this Jablonski diagram. So as I said that in chemistry, if anyone has this chemistry knowledge, so you know that there are two states of the energy levels, that is singlet state and the triplet state. Okay, so the singlet are represented here as the S and triplet is T. Okay, so this S naught, S1, S2, these are all quantized energy levels, and in each energy levels, like in each singlet energy level as well as the triplet energy level, so this is because of this p orbital means this orbitals different directions on where these lone pairs are present. According to that, these singlet and triplet energy levels are there. So these energy levels can be further, means if you look deeper into these energy levels, there are many vibrational levels which are also present, which are quantized inside these energy levels. So in fluorescence spectroscopy, we are actually moving to more means in the moving this means electrons. If you provide an energy, this electron which is present in the S naught energy level, it will move to several vibrational energy levels of either S2 or S1 on the basis of how much energy you are actually providing. Okay. Now, if it is going to the S2 energy level or the vibrational levels, on there will be a vibrational relaxation. So, from since I said that there are multiple vibrational levels inside this S2 as well. So, from higher vibrational level, it will be relaxing to the lowest in the vibrational level. So, then this is known as the vibrational relaxation. And during this period, a lot of energies, the radiative energies or heat energies, they are being emitted. Okay. Now what it can do, it can directly come back to the means S naught phase, thus by just emitting this means heat or radiative energy, or what it can do is that it can do an internal conversion from this S2 vibrational energy state. It can move to a S1 energy state, and from there it can again come to a vibrational relaxation where from there, if you from if this here also some heat is generated and some radiative energies are generated, but then after from the S1 phase to S naught phase, what emission is occurring, this will give you the fluorescence. Okay, so from the S1 energy state to this S naught state, when you get the emission, that is comes in the form of fluorescence. Now, sometimes what can happen is that this uh, this S1, from this S1, it will not directly come to the S naught phase. Rather, it can be moving from a singlet energy level to a triplet energy level, which is known as inter-system crossing. So you see, there are different time periods which for which it is happening. So the absorption is 10 to the power minus 15 second. Okay, so it is in a very small time scale. Okay, whereas if you see this fluorescence, this is in the 10 to the power minus 10 to 10 to the power minus 7 second. So these times are also very important, means in which lifetime what is happening. Okay, now, if you see this inter-system crossing, which can happen between the singlet and triplet state, again there will be a vibrational relaxation. One thing can happen is that it can directly come down from this triplet to this singlet state. Other option is that it can move to different vibrational levels of the S naught. Okay, so one thing, it can be have a vibrational relaxation, or there can be an emission from the T1 triplet energy state to the S naught state, which is known as the phosphorescence. So there are two kind of fluorescence, means normally when you uh, talk about fluorescence and phosphorescence, you see the phosphorescence is a more time taking process than the fluorescence, which has a shorter time period. Okay, because it need to have this inter-system crossing for this phosphorescence to happen. Okay, so this is the overall Jablonski diagram with which you can, so those molecules which will follow this kind of emission, this green kind of emission, they will have been this fluorescence, and those which will have this red kind of emissions patterns, they will have this phosphorescence. From the Jablonski diagram, you can actually visualize that. Now we are moving into some another kind of spectroscopy which is known as the Raman spectroscopy. So as I mentioned in the starting of today's discussion, that in Raman spectroscopy you make utilize of these different rotations of your molecules, okay, in the space. So there is the concept of this vibrational energy states here as well. Now there can be, so Raman spectroscopy is based on the phenomena of Raman scattering, due to which Dr. C.V. Raman, he also got the Nobel Prize. Okay, so what is this Raman scattering? Is that there is an inelastic scattering for this Raman scattering to happen. Means ideally when it happens is that if you have a means energy absorption, and from that in a higher energy level it is coming back to the same vibrational energy state. Okay, then that kind of scattering is known as this Rayleigh scattering. But if it is not coming to the same vibrational energy state, rather it is coming to a to a higher vibrational energy state, then it is known as Stokes-Raman scattering. Means this energy value, this green line energy value is lesser as compared to the larger, the blue line energy value. So that's why if you see the Stokes shift concept here, when we discuss that this energy of the emission is of higher wavelength but lower energy. Okay, so that if you consider that, so that is known as Stokes-Raman scattering. But if your absorption happens from, for example, a higher vibrational energy state to a higher virtual energy states, okay, means higher energy states, and when it comes emits, it comes to the zero, the lowest vibrational energy state, then it is known as anti-Stokes Raman scattering. That is, in the emission you get higher energy. Okay, so this kind of Raman scattering will happen if there is an inelastic scattering happening. Inelastic means the amount of energy that is being absorbed, that is not being emitted equally. There is some kind of difference. But for Rayleigh scattering, there is this absorption and emission is same. Okay. So the on the basis of this Raman scattering, they have this designed different Raman spectroscopy. So the what are the different Raman spectroscopy means uses of Raman spectroscopy? So the uses are you can actually detect that what are the different covalent disulfide bonds, if any disulfide bonds are present in your sample, that you can actually get from this Raman spectroscopy, because various various chemical groups will have different kinds of Raman spectra as compared to one another. So from there you can actually visualize whether the chemical nature of the molecules you can actually get out from this Raman spectroscopy, or how many hydrogen bonds are there, hydrophobic interaction, ionic interaction between the protein, and also the protein folding and unfolding processes. This all can be visualized from this Raman spectroscopy method. Okay, another technique that we use for this bins folding unfolding process, you can, as I said, that from NMR also you can actually get the idea about that. Okay, so whether your protein is folded or misfolded, means from there also you will get some kind of idea. Now there is also this Raman microscopy. So just like the spectroscopy, there you were actually quantifying the characteristics of the different chemical nature of your matter. They similar to that, there is some Raman microscopy where you can actually visualize, means the major means difference between Raman spectroscopy and microscopy. So one of the questions also come about this in your assignment. I will be when I will discussing the question, I will also go to this Raman microscopy. So it has, what it has done is that it has combined a light microscope with a Raman spectroscopy. So there will be a light microscope with which is normally now a confocal microscope, which can give you high resolution images. So what you can do is that from the microscope you can visualize your sample, and you, for example, you want only a part of the sample. In that part of the sample, what is the Raman spectra? So that is possible with the help of this Raman microscopy. You select that particular field of view and then collect the Raman spectra. Okay, so with that you can actually have 3D images, as well as you can get various information about the chemical nature or chemical nature of the particular area that you have selected under your view. Okay, so that is the Raman microscopy. Now Raman crystallography means sometimes what happens in the X-ray crystallography, since this X-rays hits the crystal and your proteins may get degraded. So this Raman crystallography, you do not have that problem. So you can actually get the chemical nature or the information out of it is that chemical changes occurring in the crystal that can be easily visualized by the Raman crystallography technique. Okay. So this is all what I actually wanted to discuss with you today. And these are some practice questions. So I will be sharing this slide. So many of these questions are repetition of your means these assignment questions, and some of them also came in your means previous year question papers. So I have taken from there. So you can look into these practice questions in your home. If you have any doubt, because if you have listened to my means 2 hour discussion, it will be very easy for you to solve these questions, and everything is there in the slide, so you can actually go through them. Now what I will do is that I will discuss about the assignment questions of week 7. Okay, so one of you have joined later, so if you have any also doubt, you can actually ask me. Okay, you guys have any doubt? So regarding the assignment, I got two doubts that I will be discussing. If any other doubt you have regarding today's discussion, okay, you got the idea, right? Whatever I discussed today. Any doubts? Okay, so no doubt. Okay. Okay, so then we can discuss about the assignment questions little bit. So the first question is the selectivity and sensitivity of a fluorescence spectroscopy is higher than that of absorption spectroscopy because of all of the following except. Okay, so this is means telling you that the fluorescence spectroscopy is normally more selective and sensitive as compared to a normal absorption spectroscopy. Why that is so? So when there is this absorption which is happening, there is also this non-radiative transition and fluorescence is happening. But as I said that it is not always that for every molecule this absorption will happen and you will get the fluorescence. So this option fluorescent substance have different lambda max of excitation and emission. That is correct, because you need to have a particular means wavelength lambda max with which you want to excite that molecule, and a particular wavelength of emission at which it will give the fluorescence. Then rigid molecules can only fluoresce because if you have a certain other molecule, this fluorescence can be quenched by other molecules. Okay, so that does not means this is also correct. Fluorescence intensity depends on the intensity of the incident radiation. Obviously, when you are giving an incident radiation, that it depends upon the incident radiation also, the how much energy it will be absorbing. But every molecule that absorbs UV region in UV region can show fluorescence. This is wrong, because as I said that all molecules will be which will have an absorption, this is not necessarily that they will form the they will give you the fluorescence. So this is asking because of all the following except this reason that every molecule that absorbs in UV region can show fluorescence. So the answer to their first question is option D. Okay, the transition zone for Raman spectra. So the transition zone for Raman spectra is saying that there are options, as I discussed. It is between the vibrational and the rotational levels. When we discussed Raman spectroscopy, I said you get the rotational information and there are different vibrational energy states, due to which you get this Raman spectroscopy. So the answer to your second question is the option B, between vibrational and the rotational levels. Now, which amino acid in GFP is not essential for formation of chromophore and green fluorescence? So, if you remember about the GFP slide where we were discussing about this, why we have this green fluorescence protein, because there are different kinds of means three amino acids which are very important, and they are serine, 65, tyrosine 66, and glycine 67. So it has in the question it is asked that which amino acid in GFP is not essential for the formation of your means chromophore and green fluorescence. So serine, we discussed that it has a role, tyrosine it has a role, glycine it has a role, but glutamine does not have any role here. So the answer to your question is option B. Okay. Then chemical events within the crystal can be obtained from which of the following technique? So in the slide when we discuss about this Raman spectroscopy, so I also showed you about this Raman crystallography, right? Where I said you that inside a crystal you can get the chemical information out of it. Okay, so it is asking chemical events within the crystal. So it is not X-ray crystallography, because X-ray crystallography it will damage the most of your means sample. After some time you will not get this chemical events of the crystal. Okay, so X-ray crystallography is not, NMR is not, Raman spectroscopy is a technique of spectroscopy, but among them this crystal, if you want to see the chemical events within the crystal, it is more specifically Raman crystallography. Okay, so the answer to your question is option D. So what happens here, you have a crystal tray, there is an illuminating lamp with which you actually get this image, and there is a Raman monochromator with which you have a single wavelength coming and bins going into this CCD camera, from where you get this Raman data, and from this microscope you can actually visualize your crystals. Okay, there is a laser light source which is falling into your crystal, and which can, through which you can actually visualize your crystal, as well as you will also get the Raman spectra with the help of this Raman monochromator and the CCD camera. So with this you can actually get the information about the chemical changes in the crystal, as well as visualize the crystal using this Raman crystallography technique. So the option is the D option is the correct one. Now here identify the correct decreasing order of wavelengths in the electromagnetic spectrum. So as we discussed, so all the options that is given here, these are not correct, because a decreasing order of wavelength in the electromagnetic spectrum means from the highest wavelength to the lowest wavelength you need to actually organize it. Okay, so that I was telling to Shayani, because she has that doubt that. So I also, when I saw this question, I also means have that same doubt. So this question is not, the options are not correct. So I will write to them, the NPTEL team, as well as to sir. So if you, any one of you have given any answer, so you can get marks, because the option here should be the radio wave greater than infrared, greater than visible, greater than ultraviolet, greater than X-ray. So these only option, but it should be like greater than, greater than. It's X-ray wavelength is not greater than ultraviolet. Okay, so this question was wrong, but the correct answer will be this: radio wave, infrared, visible, ultraviolet, and X-ray. Okay. Then Beer-Lambert's law states that. So here I am giving you the intensity of light directly proportional to 1 by sample concentration. So your answer is 6A, but I have written this because the question is not clear. If you see the intensity of light, the incident intensity of light falling in this sample, then it is the sample concentration. If it is more, then the intensity of light which will be going out, that will be lesser, right? So it is subject to what intensity of light it is asking, whether the intensity of light that is getting absorbed, because if it is intensity of light getting absorbed, then your option A is correct. But if it is the intensity of light that is getting transmitted, then that will be inversely proportional to the sample concentration. So this is also a doubt, but if you have given this A option, then you have got the correct answer. But this question was also not clear, so it can be B as well as this A. Okay, so I think both of them should be correct, because it has not written that intensity of which light, absorbed light or transmitted light. So so this is the doubt of the sixth question. then molar extinction coefficient of a molecule is dependent on. So as I said, this molar extinction coefficient in this slide when we discussed, we said that is the intrinsic nature of your matter as well as the wavelength at which you want to get the absorbance. So the correct option here is D. Okay. Which two signature negative and positive bands can one observe when performing a series spectra of a beta plated sheet? So, if you search in Google, you will directly get 218 nanometer and 195 nanometer, due to which you get a correct answer here, C option. But it can be also 216 nanometer as well. Okay, so this is also some contradictory, but since sir also discussed, so I will write to him whether they can consider whether 216 nanometer and 196 nanometer is also correct, because it should be correct. So this A and C both are means correct. So I will write to him. But yeah, so the answer what he is given has this 218 nanometer and 195 nanometer. Okay. Then Raman microscopy. So this Raman microscopy, I had just given you a diagram that how it works. So as I when I was discussing Raman microscopy, I said you that this Raman microscopy consists of this microscope part as well as the spectrometer part. So in the microscope part, what is happening? There is your microscope stage. You illuminate with a green light in your sample, from which you will get a means an image out of it, and then it is actually when it is going out, it can the scattering here is of two types, both as the Rayleigh scattering as well as the Raman scattering. So both of them are present, but you only want the Raman scattering to occur. So due to which you have a filter. Then you pass only the Raman scattering wavelengths, and it passes through the confocal pinhole to go to an entrance slit, and there is a spectrophotometer, due to which you will get a Raman spectra out of it. Okay, so you are actually selecting a field of view and you are getting a Raman spectra out of it. So the what you are doing is that this is a chemical analysis technique, because you are knowing the chemical nature of a particular region of your sample. So this is the option. The correct option here will be your option A. Okay, and then the last one is circular diachroism spectroscopy. It is sensitive to, as I said from the first when I was discussing circular diachroism, it is very useful to visualize the secondary structures of your protein. That is whether your protein has more alpha helix or more beta sheet or more random coils, so that you can actually easily visualize with the help of this circular diachroism spectroscopy. So the option B is the correct answer here. Okay, so this is all about your this week a week 7 assignment, but there are I think there are some doubts, so I will write to them. Let's see if they reply back. Okay, because I do not have the direct contact with sir as well as with the team who are making these questions, because I am here only to give you brief idea about the week's content and also help you to solve some questions, and which I am giving you in the practice questions. So my main aim is to make sure that you are getting the concepts correct. Okay, and but still I will write to them, to the NPTEL team to whom I address. So if they will reply me back, I will let you know in the next main session. Okay, and other than that, if you guys have any doubt, you can ask me. And the week 8's content, I have not discussed this that much. I have discussed this week 7's content, because last week we discussed about NMR, so due to which I got a week lag. Okay, so, but in this week you have this electron microscope. So this means basics of microscopy, it will start. Okay, so in week 8 you have that. So what I can do is that I can just share this slide also, but next class we will discuss more about is cryo-electron microscopy and how these different microscopy techniques evolved. Okay, so I will share this slide, but don't look into much into it because you can say, read it if you want to solve the assignments of week 8 because that will be helpful for you. But the thing is that we will discuss in details about this in the next class. Okay. So if you guys have any doubt, you can ask me. Mm. Any doubts? Anything that you want me to clarify, you can ask me. Ninth question of your week 7 assignment. This one, right? Raman microscopy. Okay, sorry. I actually said you. Okay. Sorry, you pointed out correctly. So, yeah, sorry for that. So I didn't saw the other options. So this Raman microscopy is actually it is giving you the chemical analysis that I discussed. Then from the figure only you see that it is an addition of Raman spectroscopy with a microscope, so the option B is also correct here. So the Raman spectroscopy is also means correct option here. Okay, and then you also add a traditional light microscope from here. So this was is Raman spectroscopy part. This is the traditional microscope. So the all the three options are correct. So sorry for that. I said you that the option A is correct, but no, all the three means combination of all this is the Raman microscopy. So the option D is the correct option here. Okay, for 9. Okay, now it is clear, Shani. Sorry for that. Yeah, I didn't saw the options. Yeah. Okay. So any other questions other than this? No questions. Okay. Then okay. So you can look into these slides that I will share you, as well as some reading materials about CD spectroscopy. I will share you in the Google Drive. You can read about those things, and if you find any difficulty, please ask me in the next session. And this session was also recorded, so you will go to you can if you visit the YouTube channel for this means course that I have created, NPTEL Structural Biology. So if you search by that means by writing my name, you will find that, and you can look into this means Shodo. I think he joined a little bit late, so you can catch up the part that I discussed with Shani before we joined. So from that video as well. Okay, and if you have any doubt, you can ask me in the next session or next Friday. Okay. So then I am ending the session today. Bye. Good night.